Okay, so we're moving on in our physics unit of EMR, and we're going to kind of break away a little bit from the concept of lenses and mirrors, and we're going to start talking about interference and diffraction. Some of the terminology we saw in Physics 20 and / grade 8, but we didn't look at it in these particular concepts. So when a light is shone on a piece of paper or a screen that has two slits in it, a scientist initially made the prediction that what would show up on the other side would be two slits. When he went through with the experiment, what happened was he saw on the background screen, he saw multiple lines, and what it's called is an interference pattern. And what you can see is that we get these dark bands and then these bright bands in between, and then a dark band, and then bright bands in between. And so the scientist that figured that out was Young, and then this concept of this monochromatic light coming into something that has two slits on it and being projected onto a background screen, it's known as Young's double slit experiment. And so in order to, again, the theory, and then he needed to explain it, what he did through all of his experiments is he came up with these conclusions. The first two are kind of like the really most important ones. It says diffraction and interference strongly support the wave model of EMR. So remember, we've looked at wave model and there's a particle model. We haven't really touched on the particle model, but a wave particle dual theory. And we said that light is EMR is through both of those. This diffraction and interference works with waves. So that's the light traveling in a wave-like pattern, not as packets of energy, but in the wave pattern. And then that diffraction is the ability of a wave to spread out as it passes through an opening. And we can see this here where we have the light waves come in like this. And when they pass through this slit here, like this, then we can see the bending pattern happen. Okay. So when it passed through the two slits in Young's experiment, it would diffract or bend around the openings, and two waves from each opening would start to interfere. So this is a single opening here. Bright bands in the interference pattern are what we call constructive interference. So constructive interference is when two waves are in phase, overlap each other, resulting in an increase in amplitude. So this is language that we definitely saw in Physics 20 when we were doing simple harmonic motions. Grade 11s just came right out of that, but grade 12s, you might have to dig into the recesses for your knowledge. Dark bands in the interference pattern are destructive interference. So that's when two waves that cancel each other and they decrease the amplitude. And so we're going to do some drawings in this spot here. We're going to have wave 1 come through. Wave A is traveling in this direction, and wave B is traveling in that direction. What happens is they meet up in the middle, and so it's the height of A and the height of B. This is A and B together, and then they pass through each other. This becomes B moving in this direction, and this becomes A moving in that direction. This is constructive interference, where we get this piece here, and this is what we're going to see as a bright band. Okay, it's a bright band in the interference pattern. Destructive interference, so again we have A is traveling, and then we have B is traveling. and then they meet in the middle. And what happens is when these heights are identical, we end up with a net zero height of A and B, and then they move on their way. Okay, so like if wave A had an amplitude of 3 meters and wave B had an amplitude of 1 meter, what we would see here then is an amplitude of 2 meters. So they cancel each other out when they go through, and this is the dark bands when we're talking about interference patterns. Okay, so we have constructive interference and we have destructive interference. Constructive interference is going to be the bright band, and destructive interference is going to be the dark band. Because when we look at a diffraction grating, I know this looks really confusing, but I'll explain it to you. So what happens is the wave is coming in this way. Here's the double slit. So this side of the experiment, or this side of the waves, is going to bend like this. Around this opening here. And then around this opening here, we get bending of light as well. Okay? When we go halfway in this section here, this is a solid piece. You think of it as the top view of a piece of paper. This is a solid piece right here. What happens is when we go halfway, this is what we call N0. And then every bandwidth out, every bright band out, is a diffraction grating of n equals 1, and n equals 2, and however many bands. But it's, if you notice it, n2 is where it's crossing here, crossing here, crossing here. Okay? Same there. And what we see at these points is we see a bright band, constructive interference. Same thing here, crossing here, crossing there, crossing there, crossing there. We see a bright band. The dark bands come where there's no interference happening. There isn't an amplification of the wave coming through. So we have these bright bands, which are constructive interference. And we have these dark bands. A dark band here, and a dark band here, and it's destructive interference. Okay, those are what we just talked about. Now, what we can also say is that the bright bands are called a maxima or an antinode. So those of you that remember anything from simple harmonic motions, bright bands are antinodes and dark bands are nodes. Okay, where destructive interference can be found. So destructive interference, there will be no light, there will be no sound. So it's only at antinodes and or maxima is the positives, and the dark areas are minima or nodes. So this bright band here would be an antinode, or maxima is the other language. And then these dark bands are nodes and or minima. Okay, and then this one here, N0, is the central maxima. So, of course, with every experiment, there's some math to go with it. And what he said, what Young came up with, is that wavelength is equal to the distance of the slits, so the distance of the slits here, and the distance from the central bright band to another band. So this from one bright band here to here. That's an X. N is the number of the bright bands. So if you're never told what the number is or you're unable to calculate it out, it says that we can assume that N equals 1. L is the length of the distance from the screen, split screen to the screen. So this part here, this is L. From the split screen to the screen that's doing the capturing, the detection screen, this is L. Okay. The other way that we can figure it out is lambda, or wavelength, is equal to the distance between the slits. So this purple piece here, or this piece, they're going to be equal. So the distance between the slits, the angle from the center of the slits to the bright band. So from this angle here, we can see here's a bright band. So we can go from the center. Remember I said we had to go from the center. So central line out. And this one here. Right in here, this is going to be theta 2. Okay, that's the angle right in here. I know you can't see it quite very well. Or if we wanted to go out to the second bright band, we would go from the center of the slits out to the band, and it would be this angle here. Okay, I'll maybe use a Sharpie to show you. So here's my line from the center out to the broadband, and here's to the bright band, sorry, and here's to my center. So because this is going out at an order of 2 bright bands, so here's my central, here's 1 and here's 2, this would be theta 2. And if I wanted to go to the first bright band and I drew that line out, this would be theta 1. Okay, so that's where the sine theta is coming from, is from the center of the slits out to the center of the bright band. And then it's divided by the number of bands that you're out, the order of bands that you're out. So here's the central, 1, and then 2, we would divide it by 2. Okay. The distance between the slits in the screen, this one here, the D here, this is also what we call a diffraction grating. And when we're back in the class, we'll work with them. So a diffraction grating simply is the number of slits that there are in a set distance. So using a diffraction grating with multiple slits instead of only 2 slits gives you a sharper image, and it's better for making more accurate measurements. I'll see if I can go find one. Okay, Mr. Jones still has my stuff. When we look at the equation lambda d sine theta n, it can be used for any diffraction calculation, but when we're looking at lambda is equal to the slit distance multiplied by the central band distance divided by the number of bands divided by the length, you can only use it when theta is less than 10 degrees. Okay, this is very, very, very key. Highlight it, commit it to memory. And then if you needed to calculate the angle, it's really quite simple. here's our so this is our distance from our, here's our center of our slit. This is our central band. And this distance here is the distance between bands. Whoops, distance. Bright bands. Always bright bands. Okay, and so what that means then, if we were looking for some angles, we could go tan theta is equal to x over L. Okay, so let's look at our first example here. Light falls on a pair of slits 1.28 times 10 to the negative 5 meters apart. One of the things you got to pay attention to quite often is they'll flip between times 10 to the negative 5 meters or 1 micrometer. Micrometers is really quite common for a distance in diffraction grading slits. So if you see micrometers, it's times 10 to the negative 6 meters. If you see picometers, it's times 10 to the negative 12. Okay, just be aware of units. The maxima, this is bright band, are 1.15 times 10 to the negative 1 meters apart, and the screen is 0.550 meters from the slit. So what is the wavelength of the light? So if we write down our knowns, remember when we read back in our notes, it said to assume that n is 1. Right here, n is the order number of the bright bands. If not indicated, assume number n equals 1. When we read this question, it just says that the maxima are 1.15 times 10 to the negative 1 meters apart. So what we're just going to assume is that from our central band up to our next band, this is the n equals 1, that this is 1.15 times 10 to the negative 1 meters. Okay, that's just an assumption we get to make. So n equals 1. Now we would be really quite quick to say this formula, and that lambda is equal to xd over nl. But we have to pay attention to this rule here, that it's less than 10 degrees, and nowhere in this question does it say what the angle is from this central band out to the first band is. We don't know what this theta is, so we have to calculate that out. That's the only way we know if we can use this formula or not. So we can say that theta is going to be equal to tan inverse of 1.15 times 10 to the negative 1 over 0.550. And when we punch that into our calculator, we see that we get 11.8 degrees. So what this means is that this one cannot be used because the angle is greater than 10 degrees. Okay? We have to use lambda is equal to d sine theta over n. Even though all the other information's been provided, this is what we end up using. So wavelength is equal to 1.28 times 10 to the negative 5 meters multiplied by the sine of 11.8, and use all your digits. Degrees divided by 1. And we see that wavelength is equal to 2.62 times 10 to the negative 6 meters. So a little bit of extra work is involved, but this is really important that we calculate this angle first. Okay, first you have to calculate the angle. All right, let's look at the next problem. Question number 2. The angle of diffraction for the second order maximum produced, so this is a bright line, by directing monochromic light with a wavelength of 4.3 times 10 to the negative 7 meters through a diffraction grating with 2.00 times 10 to the 5 lines per meter. So let's go through the information that we have. It's asking us to find the angle. We know that the order is 2, the second bright band. The wavelength is 4.30 times 10 to the negative 7 meters. And that makes sense. When we're working with visible light, we should be in that range. And the diffraction grating, this is lines per meter, but what we need is we need the distance. So it's going to be 1 over 2.00 times 10 to the 5 lines per meter. And then we see that when we do the math, meters becomes the primary unit. And we get the diffraction grating is 5.00 times 10 to the negative 6 meters. So it's asking us to find angle, easy peasy, d sine theta over n. And so sine theta is going to be equal to wavelength times the number of bright bands divided by 5.00 times 10 to the negative 6. So sine theta is equal to, when we move this over, we get lambda times n, and then we have to separate out the distance. And theta is going to be equal to the sine inverse of all of that, because this gives us a value of 0.172, negative 1 of 0.172, and all the digits that go with it. Okay, so the angle is 9.90. So from the central band, here's, this is not an accurate representation, but this angle would be 9.90 degrees. Notice it's not to the first one, it's to the second one. Okay, obviously 9.9 is very close to the main line, but this is exaggerated. This is n equals 1, n equals 2. Okay. If the distance between the slits was increased in a diffraction experiment similar to Young's experiment, how would the angle of diffraction change? So what we're going to look at, wavelength is equal to distance times the angle of the central band out to your maxima divided by the number of maxima that you have. So let's look at the angle. Let's isolate sine theta. And then let's look at the relationship between sine theta and the distance between the fraction grating. So what could we say? As this distance increases, so as this goes up, sine theta would decrease. And when sine theta decreases, theta will also decrease. Okay? So if the distance between the diffraction slits gets bigger, the angle is smaller. Whereas if the distance between the slits was decreased, the angle to the diffraction would be larger. If a blue laser was initially used in Young's double slit experiment, how would the distance between the bright bands change if a red laser was used? So if we're going to change lasers, we're going to cause our wavelength to change. And when we go back to, where did we see that? To the second page on the very first lesson, we get that visible spectrum, and we see that red light is at 700 nanometers. And blue light, I'm going to put an approximate here. Blue light is approximately 500 nanometers. Okay, so if we change our lasers, what's going to happen to our wavelength, do you predict? While I get back to my spot. Mirrors. There we go. Well, hopefully you predicted that the wavelength increases. So the wavelength right is going from 500 nanometers to 700 nanometers. So right, xd over nl, so we have the distance between the slits, we have the distance from the central band to another band, all over the number of bands, and the length from the slits to the receiving screen. If we're looking at how would the distance between the bright bands, which is x, change, let's isolate for that. X is equal to lambda NL over D. So and then it's asking us to look at wavelengths. So let's isolate wavelengths, proportional to wavelengths. As our wavelength increases, we will see that our distance from the central band out to the first bright band and subsequent bands would also increase. So as wavelength increases, so does the distance between the bright bands. Okay, so you're going to stop it here. You're going to work on these practice problems at the bottom of the page, and you're also going to look at practice problems number 1 and then number 2 to 6 on the next page, and we'll go from there into refraction and diffraction.